Hi, this is a micrograph of a metamorphic rock. We can tell it's a metamorphic rock because of the minerals that we find in it. Andalusite and sillimanite are exclusively metamorphic. What I want to do in this lesson is to consider the evidence about how this rock would form and to introduce a new idea in metamorphism called a metamorphic pathway. So for this lesson, you're going to need a copy of the Metamorphic Pathways graph in colour and also the image of the photomicrograph that you've already seen. Okay. This is an important graph for metamorphism. It shows us the stability conditions for three different types of metamorphic mineral. They're actually all variations of aluminium silicate, but they form actually noticeably different minerals. You know, these things don't actually look the same, even though they're made of the same stuff. And they're different because of the pressure and temperature conditions at which they form. So we can see that Andalusite here forms at a wide range of temperatures but fairly low pressures. Kyanite needs higher pressure to form, and sillimanite needs higher temperatures to form. So if we find these minerals within a metamorphic rock, we can actually start to get some idea about the pressure and temperature conditions which it was subject to during metamorphism. Let me add a bit more detail to this particular graph. What we can now see plotted on this are what we call the pathways. Now, metamorphic pathways are plots of how pressure and temperature change with respect to each other during the process of metamorphism. I think so far we've been looking at metamorphism as, if you like, a one-time deal, where there's a pressure and temperature that's applied to a rock, it changes, it's metamorphosed. But actually, metamorphic rocks will have been on a journey. Perhaps they'll have been buried at depth and then coming back to the surface. Perhaps they'll have been heated up by the proximity of a pluton. Either way, that creates what we call a pathway. Now, I've marked two pathways on this graph. What I've called pathway 1 in red. And you can see there are two parts of that. Firstly, where the metamorphism increases, and secondly, as it decreases. Pathway 2 also has the same increase and decrease, but perhaps the pattern is a bit different. I've also marked this point X. We'll come back to point X later. But we can see from this that there are some interesting things going on during the process of metamorphism. Let's try and explore that in a bit more detail by looking at, or by breaking this graph down. Let's ask a few questions here. So, as we've said, metamorphic pathways indicate changing pressure and temperature that occurs. What we don't have on this graph is time. We're not going to worry about that just in this particular circumstance. Different types of metamorphism, though, are going to produce different metamorphic pathways. All related, of course, to pressure and temperature. So, we have, as a result of this, two types of metamorphism. What we call prograde, which is where the metamorphic grade is increasing, perhaps with increasing depth or increasing temperature. And we have what we call retrograde metamorphism. Now, this is a slightly different, slightly new idea, where we can have metamorphism as the temperature and pressure that's a rock is being subject to is actually decreasing. Okay, let's try and read the graph a little bit. If we have a temperature of 600 degrees centigrade, um, if we have sillimanite and andalusite both stable, both being able to crystallize at 600 degrees, what pressure do you think that rock is being subjected to? Also, if we look at these, look at pathway 1, can we identify the maximum temperature, the maximum pressure that this rock would have been subject to on pathway 1, and what minerals would form at those points? Press pause and see if you can work that out now. Okay, let's see what we've found. So if we have 600 degrees of temperature, where we'll get sillimanite and andalusite is if we have about 0.25 gigapascals of pressure. So a depth there, what, about 7 kilometres down. If we follow pathway 1, we can see that the maximum temperature on pathway 1 is 600 degrees centigrade. And the mineral that we'll find forming at that maximum temperature is sillimanite. If we look at pressure, the maximum pressure is actually 0.56 or thereabouts gigapascals. But the mineral we'll have forming at that point is kyanite. So we can see on a journey through this increasing metamorphism, we can have different metamorphic minerals forming. Okay. So if this is the case, what type of metamorphism do you think is actually being represented by pathway 1? What's actually happening there? And then how are the rock cycle processes and plate tectonics actually creating those conditions along pathway 1? Firstly, for increasing metamorphic grade, and secondly, for decreasing metamorphic grade. See if you can work out the answers. Press pause now, see what you can come up with. Okay, if we look at pathway 1, we can see that there's an increase of pressure and temperature together. Now that's most likely to be formed by regional metamorphism. So if we have regional metamorphism going on, to increase the metamorphic grade, we've got increasing burial. If we increase the burial, of course, increase the depth, the temperature will increase in proportion. Now, that happens where the crust thickens up. So some type of continental collision, a convergent plate margin with subduction going on, can create those conditions. But this rock hasn't just been buried deep, it's also decreased its metamorphic grade. Now this occurs where we get uplift and erosion. Perhaps crustal shortening, continuing subduction, we get thrust faulting, bringing rocks back to the surface, perhaps erosion of the overlying rock, means it starts a journey to the surface, but we're still at metamorphic temperatures and pressures. Okay, so how does this relate then to this particular rock? We can see we've got andalusite and sillimanite together in the same rock. But we're told that this particular rock formed at point X on pathway 1. So this hasn't formed on the boundary between the two minerals. So a couple of things to consider. Firstly, if we compare pathway 1 then, that would produce this rock, with a rock that would follow pathway 2, how might that differ? What might be different features of this rock if it's just followed pathway 2? Secondly then, these minerals only form at the temperatures and pressures at which they're stable. So why then do we have this rock, remember, that formed at location X, containing both andalusite and sillimanite? Have a think about that, see what you can come up with. Okay, if we think about pathway 2 shows an increase in temperature without much of a corresponding increase in pressure. Now that really is only going to be caused by one type of metamorphism. It's got to be contact metamorphism because of that low pressure. We don't see any foliated texture as a result. We wouldn't see any sillimanite in a rock that's followed pathway 2 because the temperature doesn't get high enough. It's confined to the andalusite zone. So all we'd see would be andalusite. But this rock contains both sillimanite and andalusite. So clearly, it's been on a journey through both of those zones. So when the pressure and temperature was higher, sillimanite was able to form. But as it cooled down, perhaps the sillimanite then maybe started to become less stable. That or the amount of time the rock spent in that zone wasn't enough for recrystallization to occur, for the sillimanite to recrystallize as andalusite. Or perhaps there wasn't enough energy, not enough heat for that to occur. So what we see as a result with the presence of this andalusite is this idea of retrograde metamorphism. Metamorphism that's been actually occurs at the lower temperature and pressures than the maximum. So, to conclude, by reading a metamorphic pathways graph carefully, we can reconstruct the metamorphic history of a rock, and from it, the rock cycle processes that are going on, both on the rock and in the region around it. We do need to remember, as we've seen with the igneous rocks, that these minerals will only form at the pressure and temperature conditions at which they're stable, at which the bonds can be made to create these particular minerals. We do need to consider perhaps some examples of this in reality, but that's for another lesson.